Hello and Assalamualaikum. So we are from group 3 and today we're going to present our experiment 7, which is the Torricelli'S theorem. So these are our group members. For the introduction, Evangelista Torricelli formulated Torricelli's law in 1643. This principle, also known as the Torricelli theorem, states that the velocity of fluid flowing out of a container is the same as the object would have if it would fall freely at the same distance. This law is applied to describe fluid dynamics, especially for calculating the velocity of fluid exiting a container through a small hole. The main objective of this experiment is to identify Torricelli's relationship by comparing measured and theoretical value of the velocity, while the scope of this experiment is the volume of water used is 2, 1.75, 1.5, 1.25, and 1 liter, while 3 different height is used from the floor to the orifice.
For the theory part, as it can be seen in figure 1, the speed v of water flowing out of a hole depends on the height, which is z of the fluid above the hole, similar to the speed an object would reach, falling freely from height z under gravity. As z1, which is water level above the hole, increases, higher potential energy can result in greater flow speed. In real condition, factor like friction and air resistance slightly reduce the actual speed. We obtain Torricelli equation from Bernoulli equation, which we cancel out P1 and P2 because it is exposed to the atmospheric pressure, and V1 we also neglect it since it is a large opening cylinder. Then we cancel out Z2 because we set it as a datum, thus Z2 equals to 0. So we obtain Z1 is equals to V2 squared over V theoretical. It is a theoretical velocity of a fluid exiting an orifice under the influence of gravity, assuming ideal condition, which is there's no friction, viscosity, or other losses. So the formula is Z2GZ1, which is V theoretical is velocity of water exiting the drill hole, G is the gravitational acceleration, and Z1 is the initial water. We calculated consider for factors such as viscosity, friction, and energy losses, and it is often lower than the theoretical value for velocity due to energy losses. So by considering the maximum water trajectory distance, which is d, we obtain the velocity for calculated velocity, which is d set g over 2h, which is d is distance of the ejected water, g is the gravitational acceleration, and h is height between drill hole and...
These are the apparatus used for verification of Torricelli's theorem. How do we conduct the experiment? First, we will set up the apparatus as shown in figure 4. H1 is measured, 2 liter of water is filled into beaker, and by covering the hole using a finger, the 2 liter water is transferred into the cylindrical tank. Then Z1 is measured, finger is removed, water is ejected out. By using clay, the distance of ejected water is marked and measured. Simultaneously, time taken for water to drain out is recorded. Step 2 to 6 is repeated 2 more times to get average value. Step 2 to 7 is repeated by reducing 0.25 liter each time until reach 1 liter. Step 1 to 8 is repeated by placing the tank at H2 and H3. The results are recorded.
So these are the results that we obtained from conducting the experiment earlier, putting the gravitational acceleration as the constant, which is 9.81 meters square per second. So this is from the height one, which is 0.36 meter, using different types of volume of water, which is 2, 1.75, 1.5, 1.25, and 1 liter, measuring the initial water level, Z1, and then maximum water trajectory distance, D, and then time taken for water to drain out, D. Using the average, we're going to calculate the theoretical velocity, V theory, and the calculated velocity, which is a V calculated. And then we're going to find the percentage error. So the formula to calculate the velocity theory is square root 2 times the acceleration G and Z, while the formula to calculate the velocity calculated is D square root G over 2H. So table 2 is calculated using the same formula as table 1, but we're going to change the H to H2, which is 0.56 meter. For table 3, we still use the same formula as table 1 and table 2, but we're going to change the H to 0.76 meter.
Next, we will see discussions. In our experiment, we have 3 independent variables, which are volume of water used, initial water level, and height between drilled hole and ground. We manipulate the initial water level by controlling the volume of water used. The reason to choose initial water level and height between drilled hole and ground is because we need to investigate how height influences the speed of water flow and how far it can be ejected. We have 4 dependent variables here: maximum water trajectory distance, time, calculated velocity, and theoretical velocity. When we calculate how far and how fast the water can eject, first we can calculate velocity by using this information, and second, we can see the efficiency of water flowing system. We have 2 constant variables. We use same tap water and gravitational acceleration. This is because density and viscosity of material we use will affect the behavior of fluid flow, so it must remain constant throughout the experiment. As for gravity, it is considered constant because uniform distribution of Earth's mass and constant distance from the center of Earth.
Question number 2 asks us to relate the Bernoulli equation with Torricelli's law for this case and show all the derivation. So from Bernoulli's equation, it is the total energy of each particle of a body of fluid, and it is the same provided that no energy enter or leave the system at any point. So since the pressure at the top of the cylinder tank, which is P1, and the exit point through the orifice P2 is exposed to atmospheric pressure, thus it is considered zero, and velocity at point 1, V1 is neglected since it is a large opening cylinder. So we cancel out P1, P2, and Z1. We set Z2 as datum, thus Z2 is equals to 0. Then we left with Z1 is equals to V2 squared over 2G. So we rearrange the equation because we want to obtain the value for velocity. Thus V2 is equals to Z2G Z1, which is Z1 is the initial water level and G is the gravitational acceleration, which is 9.81 meter over second squared.
So the third question in the discussion asking about the percentage of relative error for the theoretical and measured, which is the experimental value. So the example calculation of the percentage error using the formula of absolute V theoretical minus V calculated over V theoretical times 100%, and then we're going to obtain the percentage error. For V theoretical and V calculated, we're going to obtain from the table earlier at the result. So this graph illustrates that the relative error percentage between theoretical and experimental values as a function of normalized depth h. The error decreases initially, reaching a minimum of h 1.75, indicating a better alignment between experimental results and theoretical prediction. However, as h decreases further, the error steadily increases, suggesting growing discrepancies. So the second graph data was obtained from height equal to 0.56 meter. From the result obtained above in table 1, we can conclude that the percentage error from V theory and V calculated has only slight change based on the Torricelli'S theorem. These errors have only been observed based on the height. Therefore, this minimizes the percentage error of the result. The percentage error is minimum at V equal to 1.5 liter. Thus, the 1.5 liter field cube result in smaller percentage error at this volume because the measurements are more accurate and the fluid column is less prone to a larger sources of error than a larger 2 liter field tube. So graph 3 is showing the percentage error obtained from h equal to 0.76 meter. The calculation is the same as graph 1 and graph 2. As we can see, it slightly decreases until 1.5 liter and then increases. This might be caused by several errors that we're going to discuss in the next question in the discussion.
Question is to state the source of error and method to minimize the error. So the first one is parallax error caused by eye level, which is not perpendicular to the scale when taking the readings, which will affect the accuracy. So the method is by set your eyes so that it is perpendicular with the scale when taking the readings. The number 2 is error occurred while measuring the water level height and the time taken for water to eject from the orifice. The method is to repeat the experiment 3 times to obtain the average reading. Number 3, leakage occurred while covering the hole at the cylindrical tank, which can lead to inaccuracy. So use tape or stopper to close the hole. And the last one is the direction of orifice is placed incorrectly at starting of the experiment, causing the water to flow in the wrong direction. So the method is to ensure that the orifice is correctly aligned by positioning the hole of the orifice to face directly towards the slide before commencing the experiment. Safety procedure, the first one is to make sure the direction of orifice is placed correctly before starting the experiment to avoid the water flow in wrong direction. Second one, make sure the observer's eye are perpendicular to the pointer and scale when taking the reading to prevent parallax error. Third is to make sure the floor is always dry by wiping the drop water to prevent fall due to slippery as shown in figure 9. Last one, fill up the water in the cylindrical tank carefully to prevent water from spilling out.
So in conclusion, Torricelli'S law is validated by the result of this experiment. The findings demonstrate that as the depth of the cylinder increases, the rate of the velocity also increases due to the corresponding rise in pressure consistent with the Torricelli'S principle. So these 4 are all the references that we use to complete this lab report. Thank you.